Alright, in this video I'm going to be talking about when we graph rational functions, how at times we may have what we call a hole in the graph. It says when working with rational functions, it's important to make sure that the function's simplified when looking for vertical asymptotes. What if it's not simplified? In such cases, we will have a hole. So let me show you how that works with this example here. It says for the given rational function, find any vertical asymptotes and or holes for the graph. Alright, so let's go ahead and do this. So first of all, I hope that you look at the denominator here and you recognize that this is a difference of squares. And so we can rewrite this as x minus 2 over x minus 2 times x plus 2. That's how we factor x squared minus 4. So at this point, you can see that we have two restricted values, two values that would cause our denominator to be 0, which makes the function undefined, or the answer would be undefined. So we can't plug in 2 or negative 2. Those are restricted values. Those are the numbers that you plug in and it gives you an undefined answer. Alright, so we can actually cancel these x minus 2 factors and we end up with 1 over x plus 2. So we're going to go ahead and graph this just like we normally would. It turns out this graph is just a little bit different than the original, but we'll talk about that in just a little bit. Let's go ahead and, but this is the simplified form of f of x here. So we know at negative 2 we're undefined, that's a restricted value, and we also know that we're going to have a vertical asymptote at that value. So x equals negative 2 will be a vertical asymptote. And then for a horizontal asymptote, remember we look at the degree of the numerator and the denominator. So if you look at the numerator here, if you look at our numerator here, its degree is 1. The denominator has a degree of 2. And so this is what I call bottom heavy, where the denominator has the bigger degree. And so this is going to have an asymptote at y equals 0. A horizontal asymptote. And now the next thing we want to do is find some points. We usually start by finding any x or y intercepts. So let's find the y-intercept first. I'm going to go ahead and put in the asymptotes here. So to find a y-intercept, of course we're going to want to let x be 0. So we're plugging in 0 into the function. We get 1 over 0 plus 2. That's just 1/2. So 0, 1/2 is the x or the y-intercept. Remember, a y-intercept will always have an x value of 0, which ours does. And let's go ahead and put that point on the graph and find the x-intercept. So here we want to let y be 0. Remember, f of x is just another name for y. And so we want to know, we want to solve this. 0 equals 1 over x plus 2. Now you can multiply both sides by x plus 2, and when you do that, you'll get 0 equals 1, which is a false statement. And it tells us there is no x-intercept. The other way to think of it is, this fraction here can only equal 0 if the numerator is 0. Well, the numerator will never be 0, so this fraction can never be 0. In any case, there is no x-intercept. So we need to find, normally what we like to find is at least 2 points on each side of the vertical asymptote. So we'd like to have 2 points on this side and 2 points on this side. So far we just have 1 on the right side. You can see that where x is equal to negative 1, it would be nice to know what's going on there. And so that's going to be the first value we'll want to plug into the function. You can also see over here, it'd be nice to know if x is negative 4 or negative 3, where is the graph? And so let's also plug in negative 3 and negative 4. And so those 3 additional points should help us to draw the graph that we need to graph. So let's plug in negative 1. We get 1 over negative 1 plus 2, which is 1 over 1, which is 1. So negative 1, 1 is on the graph. So we've got our 2 points to the right of the vertical asymptote there. Let's go To the other side, let's find f of negative 3. 1 over negative 3 plus 2, that's 1 over negative 1, which is negative 1. So negative 3, negative 1 is on the graph. So you can see we're down below our horizontal asymptote y equals 0. And let's find one more value, f of negative 4. We get 1 over negative 2. So that'd be negative 1/2. And that point would be about right there. Now remember, on the ends, we're going to approach y equals 0. So let's look on the left side here. It's going to go something like that. Now as we go from here this direction, the graph has nowhere to go but down. It cannot cross that vertical asymptote. We can never cross a vertical asymptote. We can't even plug in negative 2 into this function. It's a restricted value. So the graph has nowhere to go but down, approaching the asymptote there. And the same thing on the right side. As we go to the end, it's going to approach y equals 0. And again, you can see as we're going this way, it's going to have to go up. It has nowhere else to go. It can't cross that vertical asymptote, and so it's going to look like that. So this is the graph of f of x equals 1 over x plus 2. And I had already said that that's almost exactly the same as the graph of f of x equals x minus 2 over x squared minus 4. The only problem is we did say that x can't be 2. So notice on our graph we have a point at 2, and so we're going to have to take that out and put a hole there. And so the graph of f of x minus 2 over x squared minus 4 looks just like the graph of 1 over x plus 2. The only difference is this hole. And so anytime you have a rational function that's not simplified, you're going to have this kind of an issue. All right, and that's it for the example with the hole.